So this is lecture 3, chapter 3. And what I like to start with is we're talking about mass of atoms. And so we are going to be discussing something called a mass spectrometer. I'm going to have a separate lecture on this because it is one of the topics that the AP has decided to put on the AP exam. But it is an instrument that gives us some information. Okay, so again, the schematic here will be a little more explained to you as we go through this. Okay, so again, we will come back to that. So what you need to know is this is an instrument that chemists use and other professions use. It determines what we call the mass of the sample. And the unit we use is something called an AMU, okay, which stands for atomic mass unit. Okay, talking about very small things. What we are going to focus on in this class is it tells us the isotopes of the elements. It gives us actual data to tell us what isotopes we have of particular elements. So how this instrument works is it vaporizes a sample, so makes it a gas. It then rips off an electron to make it a positive ion, makes it a positive ion, and then it puts it in a magnetic field and it sees how it behaves. Okay, so again, that's what the schematic is kind of getting at here. And again, I will have a separate little lecture on that. So if we take a sample of carbon in the solid form and change it to a gas and then change it to a plus ion, it will give you a particular what we call spectra. Okay, so I'm going to draw a little XY graph here. On my y-axis, I'm going to put number of isotopes, and on the x-axis is going to be mass in AMUs. So what you would see for carbon, as this is carbon 12 and this is carbon 13. Carbon 12 and carbon 13 is something called a stick diagram. And you could see why it's called a stick diagram, because it literally are two sticks. So I have carbon 13 here and I have carbon 12. Okay. Well, since I only have two sticks, that tells me I have two isotopes. Okay. And I could then quantify these two different isotopes, so carbon 12 and carbon 13, by a relationship to each other. I could find out that carbon 12 is about 98, 99% of the carbon we have, and about 1.11% is carbon 13. So what the mass spectrometer does is give us some data as to what kind of isotopes we have. And it's all based off carbon 12, that particular isotope. So this particular isotope has 6 protons and 6 neutrons in its nucleus. So we say for every 1 proton of carbon 12, it is equal to 1 AMU. Okay, so this only exists for carbon 12. So carbon 13, you're not going to see that. So what the mass spectrometer does is says, okay, carbon 12 is my standard. It's then going to measure everything off of that. And those are the numbers that we have. So what we're going to talk about is atomic weight or atomic mass, depending upon the book or the resource. This is what we call a weighted average. And you probably know what a weighted average is because, again, you all calculate your grade in any course based on what you have coursework-wise versus what you get on your final. So that's what we call a weighted average. If it's a traditional average, you just add numbers together and divide by however many numbers you have. So we want to find the mass of an average carbon atom in AMUs. Well, because we have a different percentage of carbon 12 versus carbon 13, I can't just do adding the masses together and dividing by 2. I have to look at their percentages in order for me to figure this out. So the mass of a carbon 12 is 12 AMUs, okay? So I'm going to multiply that by a percentage, but I'm going to convert it to the decimal form. So my percentage is 0.9889 of the carbon 12. While carbon 13's mass happens to be 13.003 AMUs, and that is because it is comparing itself to carbon-12. So carbon-12 is the standard, so that's why it has a whole number relationship here. And I'm going to multiply the carbon-13 by its percentage in decimals, so it's 0.0111. I'm going to multiply that by the AMUs. And then I'm going to add these two together, and I'm going to get the overall mass of a carbon atom, which happens to be 12.011 AMUs, which, if you look at any periodic table, depending upon how many units they take it out, or digits they take it out, carbon is going to have a mass of 12.011. So again, this is equated to what we call the mole, which we're going to talk about as well. But that is what we call its atomic weight, atomic mass for the carbon. So it's based off of, again, all of the isotopes of that particular element. So we have AMUs, but that's a pretty small unit. We are literally talking how much mass those protons and neutrons have together. But we don't deal in that world, it's too small. So instead we have to have a unit called the mole, okay? And the abbreviation, which I always giggle at, is MOL. We have to drop off the E because that's way too much work to write the E down. We have something called Avogadro's number. So we have 1 mole of any substance is equal to 6.022, and it's just lopped off there, 23, 10 to the 23rd. Well, what is a mole? It could be of atoms, it could be of molecules, or it could be of formula units. So atoms are, if you have elements, that's going to be the smallest part of an element is its atoms. Molecules are coming or going to be for molecular compounds. And formula units are going to be ionic compounds. And my favorite one is, of course, formula units, because what is the abbreviation for formula unit? FU. So take a look at that. So we are going to be using Avogadro's number in a series of different kinds of calculations. But starting with grams, okay, we can take our information from the periodic table and we can calculate this. So see if you can find the number of moles of potassium and see if you can find the number of atoms. I'm going to stop the video now, and then you're going to see the answer here in a second. So here I have the solutions to these next two problems. So again, when I look off the periodic table, and if I look up potassium, and I look up its mass, essentially its atomic weight, is around 39.1, and I always round it to 1 digit after the decimal. That's how I do my calculations. So if I have 17 grams, I got to divide it by 39.1. So again, you're going to see all of my notes. I'm not really going to do proportions. Instead, I'm going to do dimensional analysis where I put the number and cancel out the units. So I end up with 0.35 moles as the number of moles. And then to go to atoms, I'm going to take Avogadro's number and multiply it. So I'm going to get a really big number of 2.6 times 10 to the 23 atoms. And the reason it's called an atom is because this is just an element, okay? And again, I'm not going to be all that particular about how you use it, but just so you have some background. So we are going to be calculating something called molar mass. I'm going to abbreviate it MM. And that is 1 mole of any substance is equal to so many grams. And it's going to be based off of, again, the periodic table and what happens to be that mass. So we're going to say 1 mole is equal to that many grams. So you might hear it called atomic mass. You might hear it called molecular mass, formula mass. It doesn't matter. We're just going to call it molar mass. But if you see that in the textbook or other locations, it's just because of what it happens to be in terms of if it's an ionic compound or if it is a molecule, whatever it happens to be. So again, what you are doing is taking the numbers off the periodic table and adding them together to find the overall molar mass of a compound. Now, do realize molar mass units are always going to be grams per mole, grams per mole. So there are 3 problems that I want you to try using the understanding of molar mass, and then I will come back in and show you the answers. So here we are again with these 3 problems. I don't expect you to know the formula for ethanol, but when we're doing notes, These are things you could look up or we could talk about in class. So C2H5OH, I would give you the formula on a test or a quiz, so please do not concern yourself with that. So all I had to do was add that up. I got about 46, so I get the grams. Now, reason I have it as 101.2 is I only have 2 sig figs here. So again, whenever we're doing calculations, you always want to go with what is given, and that's going to be how many digits you should put in your answer. So I could only have 2 sig figs here. And the problem is I can't round this to 100. That's only going to give me 1 sig fig. So when in doubt, always go to scientific notation if you need less or more digits whenever you have that in terms of significant digits. This one I had to stop in the middle to find the number of moles because that's what it was asking for. But if you were to set this up as dimensional analysis, you would just keep going if you just wanted formula units at the end. And again, this should have 4 digits because I started with 4 digits. And again, sodium bicarbonate, again, I would call it hydrogen carbonate on a quiz or a test. But in notes, I sometimes do additional stuff for that. And then methane, I don't expect you to know that either. But for notes, if I'm saying molecules, the abbreviation for molecule we're going to use is MOLEC. That's a C there. Just because you can't say mole, because that means something completely different. So I have to use Avogadro's number here, and it should be a very small number. If I'm talking only 15 molecules of methane, that's got to be a small mass otherwise. So again, those are just some simple practice problems for using molar mass.